Hello, everybody, and welcome to this week's Hubble Hangout. My name is Tony Darnell, and today we are going to be talking with astronomers who are using the Hubble Space Telescope to peer deeply into the center, into the heart of the Milky Way Galaxy. And we're going to be learning all kinds of new things about what they're finding, because they've been looking, using Hubble periodically over the past 10 years or so. They've gone back and looked at different things, and we're going to talk about what they're finding and the new research on the center of our galaxy, as well as the supermassive black hole lurking within its center. So we hope you will stick with us, and I have a lot of questions for our guests. But before I get there, let me introduce my co-host, Dr. Carol Christian. She's back from Paris, joining us now. Hi, Carol.
Hello. How are you? Sorry I missed last week.
Yeah, we missed you last week. I guess you're over your jet lag by now, right?
Oh yeah. It was a quick trip. It was painful, but it was a good trip.
Yeah, I heard that you didn't see as much of Paris as you had hoped. Well, we're glad you're back, and we're glad that you you had a good meeting. You were doing a lot of work for, I think, the future of a lot of research going on with the younger scientists. So that's really cool.
Next generation space leaders and some other groups as well. Young professionals, yes.
And you're not talking about people going out and take me to your leader. These are actually people leading in space.
We're talking next generation, so we're like Picard and Geordi. That's where I'm going.
Right.
Good.
Yes.
Yes. And speaking of next generation,
yes.
Speaking of the next generation, here is Scott Lewis. He's also joining me back to drive the internet and drive me crazy. Hi, Scott. It's good to have you. It's good to see you. Welcome back.
Thank you.
And so we want you, before I introduce our guests, I personally want you, but I also think everybody wants you to also leave questions and comments for us and our guests for the Hangout, because we've got them for the whole hour. And Scott will tell you the best way to do that.
The best way, that's what I'm also here to do. So the easiest way right now while we're live is I'm seeing a bunch of people in here already. We are using the live chat on YouTube. This is a YouTube live event. So I'm seeing everybody saying hello. So hello, everyone. And people are already welcoming you back, Carol. So they missed you as well. We'll also be live tweeting using the hashtag Hubble Hangout. So I'll be keeping up with the pictures from the press release, maybe some of the videos that are going on. So if you have any questions or comments for the panel or anything regarding the press release and what's going on towards this really awesome cluster at the center of our galaxy, please go ahead and tweet at us with at Hubble Telescope or with the hashtag Hubble Hangout. Leave comments in the live chat, and also I'll be checking out the Facebook event that we have set up for it. I see a bunch of you guys RSVP'd, so it's great to see you guys. Hopefully subscribing to our events so you'll be notified whenever we set them up, and we can keep you guys coming back for more science.
Yeah, that's a good point. I'm glad you brought that up. And if you want to find out more about these Hangouts, then the best thing to do is to subscribe to the events page on Hubble site or Hubble Telescope on Facebook. That's the best way to do it, and that way you'll get notified, and you'll get reminded when they're going to be and when the next ones are as soon as we know what they are. You can also subscribe to the Hubble site channel on YouTube. That's another way in which you can find out about all of these things. So do all of that, and if you're not following Hubble Telescope on Twitter, then are you really a Hubble hugger? That's the question.
Well, and I want to point something out real quick as far as the live chats. We have a very special guest in our live chat today. We have Zolt LeVay in our live chat. So if you've ever loved any of the Hubble images that have been released, you can thank a large part of it to Mr. Zolt LeVay. He is a fantastic wizard when it comes to putting out our images.
That is a great point. So this is actually something that I think came out of the Hubble Heritage. He works on that, Zolt does. And Carol, what is a Hubble Heritage? Can you give us a little background on what that is?
Sure. A number of years ago, a group of us, including Zolt, were noticing that there were a lot of images and a lot of data in the archive that were being used for science, and some of them were really spectacular imagery, and if we could bring those forward to the public, we would like to do that. Sometimes it required maybe an addition of an observation of an additional filter to round out the color suite to really demonstrate the astrophysics. In some cases it was just reprocessing the data and putting together imagery that was really engaging. Also, the group has done things like we observed the comet that went by Mars, a few other comets. We've observed Mars at close.
Was one of the most recent ones, if I recall.
Right, and a couple of other interesting phenomenon that sometimes amateurs observe as well. And we also have had activities often associated with our releases. And I have to say that in addition to getting additional data or bringing data forward from the archive, there have been a lot of scientists have done science on those observations as well. We're doing quite well as far as science productivity. So we have great public interest, science productivity, and really pretty images. So what more could you like?
That's right. What more could you ask for? Okay, well, great. So, yeah, the Hubble Heritage is a really important project that's going on at the Institute. If you've ever seen some of the really gorgeous, beautiful images that have come out, particularly last over the Hubble 25th anniversary, a lot of them were due to our friend Zolove and the Hubble Heritage team. So that's very good. So that brings us to this particular image for today. A press release came out about another set of Hubble observations of our galactic center, and here to talk to us about these images and so much more in the center of our galaxy are today's guests from the University of California, Los Angeles. Apparently there's a group there, and what they do at that group is they look at the galactic center. See, it's right there in their thing. It says Galactic Center Group. And joining me is Professor Mark Morris. He is a professor there, as well as Dr. Tuan Do. He's also a research scientist there. Welcome, guys, and thank you for joining our hangout.
Hello.
Yeah.
Hi. Yeah.
And it's actually kind of chilly out here in LA. It's only like in the
I
upper
don't even want to
60s.
hear it. Don't even start with how chilly it is. Oh,
It's been kind of chilly. It's like 25 out.
Oh, jeez.
yeah, nice. Okay. Well, I'll just ignore what that is all about. So, we were talking a lot earlier before the hangout started about some of the background of these images and some of the observations that we're doing, and we're going to get to a lot of that today. But these guys were telling me there's an awful lot of interesting stuff going on at the center of our galaxy, some of which you've learned about already in previous hangouts and other sources at Hubble site. But one of the important points is that the Hubble Space Telescope has been looking at our galactic center for a long time, and since I think 2005, according to some of what we talked about earlier today, they've been looking at various epochs. They've been going back and looking periodically at the center of our galaxy, and we're going to talk about why they were doing that. But let's talk today specifically about today's image. And Tuan, why don't you tell us a little bit about what the release was and what precipitated it? What sort of research were you hoping to get done from that?
Sure. So
Don has it up.
Okay. So the reason for this image is that basically because of the new instrument on Hubble. So it's not so new now, but in 2010 it was new with C3, and in particular the near infrared instrument.
Everybody's favorite camera, yes.
Exactly. So it provides a really nice high-resolution image of the center of the galaxy over a large field. So because the galactic center is actually quite close, it's pretty big on the sky. So before, from the ground, it was very difficult to see individual stars. And we can see a lot better from the ground if we use something called adaptive optics, but adaptive optics has a very, very tiny field of view. So you can't see the whole cluster.
Well, yeah, but to be fair, Tuan, so does the Hubble. It has a very narrow... Is this a one-shot thing of the entire field of view of Hubble, or is it a mosaic?
It's a mosaic. It's a mosaic of 9 observations from Hubble. But for the equivalent, how many would we need to do if we do adaptive optics?
It would be hundreds.
Yeah, many, many hundreds.
Why the difference? Because of the exposure times and the noise, or why?
Sorry?
Why would there be so many more using ground-based adaptive optics?
It's really tiny. So the field of view from adaptive optics is basically 1/200th of the field of view of that image. So it would just take forever to be able to get such a good image, basically, over such a large region of the sky. So I think Scott has other images to see what adaptive optics look like, which I guess we can look at later. But basically, you want to concentrate on looking at the places where you need adaptive optics the most, which is at the center, the very center of the cluster where the black hole is. But then use Hubble for everything else, which is further out from the black hole to get a whole sense of what the cluster, the star cluster at the center of our galaxy.
So for those of you who are just starting out looking at the night sky, if you want to know where the center of our galaxy is, it's best seen in the northern hemisphere in the summertime. And if you look toward the constellation of Sagittarius, that will be the direction of the center of our galaxy. And this is just one tiny slice. And if you don't know what adaptive optics are, these are things that are primarily on ground-based instruments or telescopes, and what they're designed to do is to correct for atmospheric distortion. And so if you've ever seen some time-lapse of observatories where they've got a green laser or some kind of laser shooting up, then they try to correct for the distortion of the atmosphere before the light hits the telescope. And so Scott is zooming in now on the center of our galaxy, and it started by looking at in the constellation of Sagittarius. So why don't you tell us a little bit about this animation, Tuan?
So this animation zooms in from the night sky you can see with your eyes at very large scale into the very center. There's a step in between, right, where you see oh, it went away, but there's a step in between in the zoom where, so in this night sky you can see these constellations near the galactic center. So I always like the teapot because the teapot is really easy to spot, and if you can spot the spout of the teapot, it points straight at the center of the galaxy. It's not very interesting to your naked eye because it's just a blank black spot in the sky. But that's because a lot of dust is basically hiding the center of the galaxy. And then when this video zoomed in and you saw the pink stuff, so that's basically with Spitzer, which is an infrared telescope, which can see through a lot of the dust. But Spitzer, of course, is a much smaller telescope than Hubble, so that's why when you zoom in, so the bright spot in the center is the nuclear star cluster, what we call the nuclear star cluster. It's very, very compact. You can see that it's sort of just the central part of the Spitzer image. But when you zoom in and you can see the Hubble image, it resolves out into individual stars. And there are, this Hubble image at the end, there's about 500,000 stars that Hubble can see in this image.
Okay. So Mark, give us a little background, a little bit of 101, Galaxy Milky Way Center 101. Tell us a little bit about our galaxy center. First of all, how far away is it? Why is the infrared such a good wavelength for looking at these things?
Sure. Well, our galactic center is 25,000 light years away. So the light we're seeing started off 25,000 years ago to reach us. And we use the infrared to study the galactic center because the visible light that most stars are emitting there can't get through to us. Only one photon in a trillion can get through the dust to reach us. So we have to move into the infrared, which the Wide Field Camera 3 can do. And there we get about one photon out of every 10 that can work its way through to us. And that allows us to see the stars that are present in the galactic center. And as Tuan said, we see millions of them with this deep image using the Hubble Space Telescope. The density of stars at the galactic center is enormous. For every star you can see in our nighttime sky from the Earth, if you were at the galactic center, there would be 1 million stars for every star we can see. So the whole sky would be completely peppered with stars, and that's a statement for how dense the stars are packed together there. Even so, the stars aren't crashing into each other like a destruction derby. They're still pretty far apart. But from our distant perspective, as we try to image them, there's stars that appear in projection to be completely on top of each other all over the place. They're one of the reasons why we need the good resolution that the Hubble Space Telescope has, and even better resolution we can sometimes get from the ground-based telescopes using adaptive optics, is that we need to separate out the stellar images since they're so closely packed together in the images we make.
And that's something you get from Hubble that you might not get from, say, a ground-based telescope without adaptive optics.
That's right.
that. So the galactic center is roughly 25 to 27,000 light years away. It's packed with stars, but if you looked at this center through the Milky Way or through optical wavelengths, and in fact, I would encourage you, if you guys can actually find really dark skies, to try and look up on a summer night and see the arc of stars that is the Milky Way. It's absolutely stunning. But if you look toward the direction of Sagittarius, you're not going to see a whole lot, but just a big, tightly packed ribbon of stars. And I guess light is scattered at optical wavelengths, right, Mark? If you tried to look at this through a regular telescope through your eye, or maybe just through a regular CCD that didn't have infrared filters, you probably wouldn't see much except the dust that's in between us and the center, correct?
That's right. It's just a big black spot. What you can see towards Sagittarius are what are called the great star clouds of Sagittarius, because the dust is confined to the thin disk of our Milky Way galaxy, but the stars are extended into a large bulge. And we can see the stars that are above and below the center of the galaxy quite well. And those are the great star clouds of Sagittarius that you can see with your naked eye as a luminous glow above and below where the galactic center is located. But right where the central mass concentration of our galaxy is, you see absolutely nothing. It's all just a black band because of the dust.
Okay, I once heard a rule of thumb that it was that on average, now obviously that's not true of every star in the galaxy, but on average there is a star about every light year. If you take the whole galaxy as a whole and you sort of average it all out, there's a star about every light year. And obviously in the galactic center that's not true. They're very closely packed. So Jimmy Hebb is asking on YouTube, how far would the stars be on average from each other in the center of the galaxy? And I'll let either one of you answer that. Do you have an idea?
Well, just on the basis of the density, they'd be about 1/100th of a light year apart from each other, which is several thousand astronomical units, where an astronomical unit is the distance between the Earth and the Sun.
Wow, so almost as far away between each other as maybe Planet 9 is. We'll have to see. That's what we were talking about Mike Brown with a few weeks back on. So so should we? Okay, so they're pretty close together, pretty far. Lots of dust, lots of gas in there, and because you guys work with galactic centers in plural, I'm sure. How we know a little bit about, we've talked a little bit about in past Hangouts about active galaxies. Is our galaxy an active galaxy? Does it have an active core? And if, well, let me just start there. Tuan, you want to answer that?
No, actually, our galaxy is kind of a WIMP in terms of the
a WIMP?
Extragalactic galactic centers.
Sorry, Tony. Yeah, we're
as
kind of
galactic centers go, we've got a WIMP. Okay.
Right. In terms of luminosity from the black hole at the center, right? So other galaxies have stuff falling into their black holes at really high rates, and so the black holes, because of the stuff that's falling in, glows and emits radiation in all wavelengths. We see them very brightly, so they're called active galactic nuclei. But our galaxy is very, very faint. Only like a trickle of gas falls in, and so it looks like a candle kind of in the sky, actually. It just flickers. So
if we try now, most active
galaxies. But it has a black hole. At least we have a black hole.
Well,
let's
go ahead and talk about our. So I guess it's true. Well, you guys can clarify this, but most astronomers think that every galaxy has at its core a supermassive black hole. Why don't you tell us first what a supermassive black hole is, and maybe a little bit about ours, and then whether you think all galaxies do.
Well, a supermassive black hole is probably defined as anything over several 100,000 or over 1 million times the mass of our sun. I guess there's no really widely accepted definition. But it's true that almost every galaxy does have such a black hole at its center. And the masses of these black holes extend all the way up to billions of times the mass of the sun. And I think the most massive one being discussed today is approaching 10 billion times the mass of the sun, which makes our hometown black hole at the center of the Milky Way kind of small at only 1 million, or 4 million, I should say, times the mass of the sun. That's by the solar system standards, that's enormous. But by comparison with other galaxies, for example, our sister galaxy Andromeda has a black hole that's much more massive by, what, a factor of about 5.
Yeah.
And
the galaxy itself is larger too, by about 2.5 times, right, or something like that. It's pretty,
something like that.
Yeah. Well, so with the supermassive black hole being there, we know it. Well, how do we know it's there? And I think that's a good segue into something I think we can show people. So how do we know? And this goes back to your observations as well. So how do we know there's a supermassive black hole at the center of our galaxy? If it's not feeding, and if it's wimpy, and it's not living on a lot of cosmic rays and all of that kind of stuff, how do we know it's there?
Oh my gosh.
Right. So there's a few ways, right? So there were signs that probably had a supermassive black hole way in the 70s, right? When the first radio observations were made, right?
Yes.
So there was an unusually strong radio source at the center of the galaxy. In fact, it's the brightest radio source in the constellation of Sagittarius, which is why the black hole is also called Sagittarius A star, because that's a radio designation.
That's the name of our black hole, right?
That's it. Yeah.
That's what the radio astronomers named it, yeah.
Yeah.
They got first dibs, huh?
And it's not like In Contact. They don't actually listen to the radio. It's many of my radio astronomer friends. They love taking that picture like In Contact, but they're like, no, it's so bad. It's so wrong. That's radio. When we talk about radio, we're just talking about really long wavelengths of light, as opposed to
No music.
Well, I mean, I guess you could jam out to it if you know.
Yeah.
It varies in time, so it does make its own music. Yeah.
Okay, so
It's like cosmic dubstep for all you young kids out there.
Okay.
Yeah, well, it has a frequency. It has a power at every frequency, and that actually is something called red noise. So it's interesting. Yeah, you can hear it. It's like waves, basically. Yeah. Anyway, so that was.
I want to take a look again at that zoom in, and then there was an image that you sent Scott right before we started the hangout that you said would be a good dissolve into the other after the zoom. So let's take a look at the zoom, and then we'll take a look at the image that it should dissolve in, and I want you to show us where the black hole is when we get there.
Sure.
So here we are zooming in to the center of our galaxy. We're passing through some dust. And now we're through some dust and getting ever closer through to the center of our galaxy. And there we are. Okay, so this was the Hubble image of the galactic center. There's where our supermassive black hole is. SAG A star, also known as not wimpy black hole. That should be our drinking game word, by the way. Wimpy.
Black hole.
Yeah.
You want to see an active galaxy? It's gonna be me on all this coffee I'll be drinking.
All right. So now there was an image that Tuan had told us about. Can you put that up, Scott?
Yeah.
And he was actually pointing out within that image. There it is. Okay. Yeah. Describe to us this image, Tuan. And
okay. So this image is probably basically inside that circle you saw at the end of that zoom. The end of that zoom was not at the black hole.
It just pointed to where it was.
So now you can zoom in further. So you see all this red stuff, basically it's a lot of dust at the galactic center. And it happens that if you zoom into the very center of the image, there's this thing that looks really red in the center. And that spot is the black hole. So, so where Scott has the cursor, that's the near-infrared emission from the black hole. So from stuff falling in, and we can tell that that's the black hole in a few ways, actually. You can tell it from just the imaging because it looks different than a star, right? It looks very red. Also, if you just take images of this over time, like over basically hours during the night, you'll see that the little red dot flickers. So this is what I mean by that it looks like a candle, is that it looks just like a candle. It just flickers in and out at night, whereas the stars are all steady in light as well. But the really cool thing is that all those stars you see around that red dot, they all move around it. And over time, you can track the motion of the stars. And using just Kepler's laws, you can say, what mass must those stars be orbiting? And it turns out the mass has to be 4 million times the mass of the sun, which is crazy, crazy high.
So 4 million times
anything else
based on
except a black hole, because that much mass concentrated into this tiny volume would have manifested itself in some visible way if it were something besides a black hole.
Oh, that's a good point. So we would see this at some wavelength if it were that small or if it were that dense and not a black hole. We would see some radiation coming off of it by then.
Right. You might wonder why the black hole is not black. We're looking at something that we see in the infrared here.
I am wondering.
We're not actually seeing the black hole itself. What, as Tuan said, is what we're seeing here is the stuff falling into the black hole. As it falls in, it gets hotter and hotter, and its last cry for help, I guess, is to emit infrared radiation as it goes through the black hole's event horizon.
Okay, so is this, what wavelength is this? Are we in primarily the infrared here?
Yeah,
Yes.
so this image is taken at 1.6 microns, 2.2 microns, and 3.8 microns. So,
Okay, so we're looking at heat, essentially, as material falls into this black hole. What if Chandra, first of all, can Chandra, an X-ray, it's an X-ray telescope, see anything when it looks in the center of our galaxy? And would we see anything in X-rays if we looked at it with Chandra? Or
Yes,
something?
good question. In fact, Chandra discovered the black hole with a 1999 observation. It's been studied extensively now with Chandra ever since then, so for the past 18 or 17 years. And it puts on quite a nice light show in the X-rays. The infrared variability is continuous, as Tuan was saying, but in the X-rays, we get a big flare from the black hole about once per day. Otherwise, we don't see much, except this low-level, weak X-ray source that doesn't vary.
What do you think that is? Why do you think it does that?
Well, that's the big question that theorists and observers are struggling with, and there's a lot of observations underway, including one that we have scheduled for this coming summer, to try to observe simultaneously with the Spitzer Space Telescope in the infrared and the Chandra at X-ray wavelengths to see, by comparing the two wavelengths, what might be going on there. There's many theories for what might produce that. Basically, it's the instabilities in the stuff falling in. It could be magnetohydrodynamic instabilities. It could just be
like that.
a variable mass inflow rate. It could be a jet coming out of the black hole. A lot of good ideas, but nothing that we can really point to with any confidence.
Okay. Well, chunky chest.
You okay?
Sorry, that just tickled me to say that. Chunky chest from
Pull it together. We're professionals.
All right. He's asking a relevant question, and it's a good one.
It is a good question.
That's kind of like Bodie McBoatface. When I first heard about that, I couldn't stop laughing. If it's effectively black, could the flickering be a form of lensing? So let's talk about that. There's obviously when a black hole is in the area, gravitational lensing might have some role to play. So is there anything that flickering? I mean, you're kind of alluding to the fact this is stuff falling in, and the periodic X-ray bursts and things like that might be periods of things falling in. What about lensing? Does that affect anything that you see in these images?
So lensing, there's different scales of lensing. Right, so we don't have high enough resolution to see the lensing of stuff that's falling in. So basically, if you had higher resolution, what you would see, which the radio folks always call the black hole shadow, it's literally like a black spot in the sky, and then stuff as it's falling in, you can imagine that's got a ring of stuff. As it orbits, basically the last part of the black hole before it goes into it becomes black, and that stuff will all get lensed, right? So this ring will look really funny in the sky because of the lensing from the gravitational field of the black hole. So it's true. It definitely happens. It also happens on slightly larger scales too, right? So if a star happens to go behind the black hole, now not like right behind the black hole, but it's just like
maybe off to this a high, little bit above it or something, behind and above.
Yeah. So if the black hole is here and the star is here, and you are observing the sky, you might see the star instead of behind the black hole, like over here, for instance, or over here. And so as the star moves behind the black hole, you'll see that somehow images of the star in the sky seems to be shifting, not the way you'd expect if the black hole wasn't there. And so that's a type of lensing that we might be able to observe, because if you look at the stars long enough, you can say, oh, suddenly why did this star appear and disappear, right, as it moves behind the black hole. And so that's something that could be searched for in the future. It's obviously very hard because there's so many stars.
Right.
How do you know which star is the one that's lensing?
Yeah. I've always wondered that anyway. Whenever we see anything from a gravitational lens from a galaxy cluster, they're able to pick out these different galaxies, 2 or 3 sometimes in the same image, and I'm always wondering, how do you know it's the same one? But they have these models that tell them, and they are able to say that's the same galaxy here.
Not a model like me. Not that type of model.
Yeah, I really hope
Computer model.
Computer simulations. Yeah.
Right. So they're able to tell that, and the way they do it to me is mind-boggling. But I want to get back to a minute about this.
I'm raising my hand.
Carol's turn.
Wait for it, Carol. Carol, yes.
She's got 2 weeks of questions.
My question or comment is, we talked about the fact that we have such a wimpy black hole, but it's pretty active, and it has a lot of things going on that can actually be observed with our ground and space-based telescopes. So if we were in a galaxy that had a really active black hole, that would be a pretty overwhelming observational environment, I would think.
Absolutely, and there's evidence that our black hole has been active in the fairly recent past and in the distant past. There's evidence that the black hole underwent a huge outburst about 100 years ago, and we see X-rays propagating out from the center, going through the central zone of our galaxy and causing fluorescence that's moving outward from the black hole. And the timing of that would have been about 100 years ago. So there might have been quite an event. It's too bad Hubble wasn't around 100 years ago. That would have been spectacular. But there also
one Hubble was around then, but not the Hubble Space Telescope. Just the man, not the legend.
Right. Okay.
About 4 million years ago, there was that's when all the young stars around the black hole formed. A big cluster of about 10,000 times the mass of our sun altogether came into being. That must have fueled the black hole copiously, and that must have produced a tremendous outburst of energy. And that would have looked like an active galactic nucleus when that happened.
So I know that it's proportional to the stuff falling in, this active galactic nuclei business, where it's basically a function of how much stuff is falling into the black hole and getting energized as it does so. Being 25,000 light years away, that doesn't necessarily protect us, does it? I mean, that could be a big deal if it were a big enough event, wouldn't it? How safe, I guess my question is, Earth from one of these really big active galaxy cores?
Well, I guess there's a lot of personal opinions on this, and my own is that we're pretty safe because we're so far away. 25,000 light years is a good.
So that's far enough that we're cool. We're not gonna get blasted by gamma rays and X-rays.
No, it could probably have an effect on the upper atmosphere if cosmic rays or X-rays were to rise by a factor of 100,000 or even 1 million, blasting our upper atmosphere. But I think we're pretty protected.
Because we've all seen these jets, right, streaming out of these centers of these galaxies, huge X-ray jets coming out, but they don't all come straight out that way. I mean, we're lucky that we're in the plane of the galaxy, but surely they go out sideways too, right?
Yes, there are some galaxies in which the jets go out in the disk of the galaxy.
Oh, see, that would really suck.
They don't get very far
Yeah,
because
we'd be having a bad day if it came our way.
Okay, well, I'm just trying to set the stage here because we should be thankful that our black hole is wimpy. Okay? And then and we there you go. And however, so nothing is falling in right now. However, I heard a couple of years ago, and we talked about this before the Hangout started, that there was a gas cloud that was circling around the center of our galaxy, and it was supposed to fly into the black hole by now. And Twan, you were telling me a little bit beforehand, before we started, that event turned out to be not so exciting as everybody had hoped, right?
Right. Yeah. So
Don't set the stage in a rather lame way, but you can maybe talk more about this gas cloud and what it was supposed to do and what people thought.
Yeah. So so I guess it would be so in 2012 there was a detection of this object that was really, really red. So it doesn't look like a star, and it seemed to have a lot of gas in it, and it was on an orbit that basically was pointing straight at the black hole, right? So then everybody got really excited because, oh, so now if this is a big gas, as a little gas cloud, if you can see it fall into the black hole, maybe you'll see some really cool black hole physics, right? If you dump a lot of material in, you might be able to investigate black hole physics. So basically, we're all waiting for fireworks in 2014. That was the year when this gas cloud is supposed to reach closest to the black hole and get all torn up by the black hole, and then all the stuff was supposed to fall in. And so every telescope on Earth, I think, that could observe the galactic center was trained at the galactic center in 2014. It's very exciting. There was a false positive for the magnetar, but after the maybe it's a fun story. So everybody was like on edge to see this thing fall in, right? And then one of the X-ray the gamma ray telescopes triggered and said there's something coming from the galactic center, and so everybody got super excited that it might be this gas cloud, finally falling in. And it turns out that they found a magnetar, which is this really it's an interesting object. It's like a compact, basically remnant of an old a star that died, but it emits extremely strong radio and X-rays, and so, but it's not the black hole. So, but it was discovered in 2014. Everybody was looking at it.
Yeah. Oh, so it was a false positive then.
Exactly, and it turns out if you track this object, this thing that was supposed to be a gas cloud, what happened in 2014 was it went, so the black hole's here, it went by the black hole, and then it went straight out. So basically, nothing happened. It's still unusual, and it's still interesting to study because it's very different than a star, but it seems like there must be something inside of this gas cloud that's holding the gas together as it's coming by the black hole, and so that's why the gas didn't get torn up and fall.
Okay, and that's what Mark was talking about before we started. But before you say anything, Mark, Scott, can you put that image back up, the zoom in, and the one with that we were talking about earlier, and because you can see the cloud in that image, and then I'll have Mark sort of tell us why they think it wasn't just a gas cloud.
You want the full zoom in, or do you want the final?
The final that image. Sorry, if you could just zoom in on that, and then the gas cloud I think is visible in this image.
I think it's right.
Yeah.
No, that's where it is. That's right. And this is as Tom was saying earlier. It's an image taken in 2005 from using adaptive optics from a ground-based telescope, and that red blob there is the gas cloud that was hurtling toward the black hole. The black hole's right at the center of the image, the other red spot. And if it was a gas cloud, it would have been completely annihilated by the tidal forces of the black hole. But the fact was, and we observed this quite a lot as this swung around the black hole, it's still there, and it's now moving away, and its integrity is intact. It has not been disrupted, and that means it has to be held together by its own self-gravity, and that's probably then a star.
So if it were only a gas cloud, then it should have fallen in, as everyone thought. But because it didn't, there must be something else there, and you guys are speculating now it might be a star embedded in there.
Yeah, there's lots of interesting theories actually about what could be inside of it, right? One of the one theory is that maybe it's something called a protoplanetary disk, which is when young stars are forming, they all the sort of, I don't know what they call it, the natal gas that was forming the star, they make this disk that's around the star, and so it obscures the center of the star. And then these protoplanetary disks later can form planets. That's which is why they're called protoplanetary disks. But this is in a very early stage of star formation, so they're hidden. Another idea that has been thought is that maybe it's actually two stars that merge together to make one star, and the merger is an event that basically throws out lots of dust and gas, and so that's why you get this big cloud around the center as well. But both theories rely on the fact that the center is something really massive to hold it together.
Okay. Well, we're getting lots of good questions coming in. Scott's getting them out here in front of me, and I'm going to get to all of them. But before I do, I just want to talk a little bit about some of these orbits that we've actually seen. I mean, there's actually observations of these stars, not of the one that Mark was just mentioning about that's associated with the gas cloud, but there's actually, because one of the ways in which, I think it was Mark also saying this earlier in the Hangout, that we know the size of the black hole based on the orbits of the stars around it. And Scott, if you when you get a chance, if you could put that up, and
way ahead of you.
Yeah, there you usually are. There we go. So, Mark, can you describe this to us? What we're looking at here?
These are the actual orbits that we've determined by watching the stars move. We've been following the stars for the last 21 years, and these are the actual orbits that we fit. They're all the kinds of orbits that Johannes Kepler would have described. They're elliptical orbits orbiting around the black hole, just like the planets of our solar system orbit the sun. The black hole dominates the gravity in this region. Look at this scale on the right. This is a really tiny area of the sky. The whole picture is 1 arc second, which is
that's 0.1
typically the
arc
size that a ground-based telescope, the single pixel of a ground-based telescope's images. And yeah, we've been able to, using
I've seen some of this data before, but I guess I didn't really appreciate that you've actually seen several of these objects complete orbits, or nearly complete orbits. And
that's
they keep
right. I think
that's amazing.
At the moment, we have a couple of stars that are fully complete, and closing in on a third, and it won't be long before we have a lot of these. And that's important because these orbits, we're looking for these tiny deviations from pure Keplerian orbit to measure the effects of general relativity, or to measure the effect of any extended dark matter distribution that might be around the black hole.
Of course, because those things would affect the orbits themselves, the dark matter distribution, as well as the and the relativistic effects. But for the most part, to get a rough idea of the size of the black hole, you just use Isaac Newton, right, and just sort of invoke the orbit trajectories and figure out what it must be that that would take to make these orbits happen, right?
That's right. 350-year-old physics is adequate to do this, John.
Good. Okay. Well, this is this animation. There's also actual images of stars moving around that blow me away too. I think they're also from Keck, which is a ground-based telescope in Hawaii. But this is how we know the black hole is there, and also roughly how big it is based on these orbits. So we've been looking at this thing for a very, very long time. Hubble has been looking at it for a long time. And I want to get to a couple of questions because there's some good ones here. I want to go all the way back to AstroGirl1 USA, who asked at the beginning. Welcome back, by the way. She's always there every week, and it's good to have her here. She's asking, and this is with regard to the star density, I think, in the center of the galaxy. Are there any solar systems in the core of our galaxy? What do you think?
That's a good question. Okay, so we can't detect planetary systems yet at the galactic center because it's really far away. But if planet formation happens similar to here, there probably are planetary systems at the galactic center. There is one difference, which is that because of the super high stellar densities, it seems unlikely that we would have things like Pluto or like Kuiper Belt, maybe, because stars would just pass by rather frequently and would disrupt the orbits of planets pretty easily if they weren't very close to the central star.
That's a good point. If things are hundreds or thousands of AU away, then they're going to probably get perturbed by passing stars coming through, or ripping off the outer neighborhoods of those solar systems. So it would be pretty chaotic, I could imagine. But that doesn't preclude planets being there. That's good to know. And I wouldn't necessarily want to comment on the habitability of said planet out there. But the night sky would be amazing if you could figure out a way to survive there. That would be.
That's right. The UV radiation alone would be awful. But,
you need a nice ozone layer, some pretty good banana boat sunscreen to get you through the day there, I think. So John Southern, who is asking, this is back when we were talking about the size of the black hole, the supermassive black hole. He said that'll change with the merger of Milky Way and Andromeda, which means I want to talk about that a little bit. So Andromeda is our closest galaxy, and at about 2.5, or it's not our closest galaxy, it's our closest galaxy like us, I guess, the spiral galaxy. And it is in about 2.5 million years, it's heading right for us, and we're heading right for it. And we will probably merge. Let's talk about galaxy mergers and their effects on these black holes and actually on the galaxies themselves. So what do you think's gonna happen when Andromeda and the Milky Way collide?
Things weren't bad enough.
If things weren't bad enough, in 2.5 million years, we're going to have a really bad day.
We got more time than that. It's actually 2.5 billion years.
Billion? Oh, it's 2.5 million. Where's the 2.5? Is it million light years away?
Billion.
Okay. All right.
The
billion. Sorry, with a B.
They will merge apparently. The details of the merger are still being worked out because we don't know just how fast Andromeda is moving across our line of sight, and that will affect how the merger takes place. But they probably will merge, and when that happens, the black holes will do something interesting. The Andromeda's black hole, which is the more massive one, and ours, will spiral towards each other because of a phenomenon called dynamical friction. The stars that they scatter as they move through this merging ensemble will cause them to lose angular momentum, and they'll spiral towards each other, and eventually they'll probably merge and create an even more massive single black hole. That may take a while, and that'll be a pretty spectacular phenomenon, and if gravitational wave detectors are around 2.5 billion years from now, they'll see some rather impressive gravitational waves from that event.
You segued in beautifully to that. So now that we can, and this comes from a question that was raised, where'd it go? There's been a bunch here. Dabasish Garami, he's asking about gravitational waves. Now that we can detect them with LIGO and presumably with LISA, if we all get lucky, what can we learn from the center of our galaxy from gravitational waves? Is there anything you guys are excited about with that new ability? And you've already talked about we can certainly see supermassive black holes colliding from centers of galaxies, but from your perspective in studying the center of our galaxy, can gravitational waves teach us anything?
I think it teaches you about the things you can't see with light, right? So, for example, so while the Hubble images are really impressive and it can actually get really faint, there are objects that are actually many objects. Most of the mass of the cluster is actually below our detection threshold just because it's far away. And in fact, as objects that can be quite massive are also invisible. So, for example, neutron stars or stellar mass black holes. Right, so because the star cluster, we didn't get to talk very much about the star cluster, but the star cluster is about 10 million solar masses. So it's a huge star cluster, which means that many generations of stars have come and gone. right? So that means that they leave relics. When stars die, they're these they leave remnants. So either neutron stars sometimes, or white dwarfs, or small black holes. So these are stellar mass black holes about 10 times the mass of our sun. But we have no idea what that population looks like because we can't see them, right? And so gravitational waves offers you a different view of these kind of objects, because if you can see, say, a neutron star and neutron star merge together, they will produce gravitational waves, and you would detect them, and you would now know something about the neutron star population. Or if two black holes merge together, like that gravitational wave detection that LIGO had, then you will know something about how many stellar mass black holes might be at the galactic center.
There's a popular theory that the central supermassive black hole is surrounded by a cluster of maybe 10,000 stellar mass black holes, the remnants of all the massive stars that have lived and died in the past in our galaxy.
Wow.
If that's the case.
They're sort of slowly accreting toward the center, huh? That's kind of cool.
Yeah, and they must interact with each other once in a while, and if one of them happens to wander close enough to the central black hole and be swallowed, that would emit a tremendous gravitational wave signal that LIGO could certainly detect, and that would be really exciting.
It's really amazing how that just opened up a completely new sense for astronomers, didn't it? This ability to see gravitational waves. It's like getting another set of eyes that are like completely tuned to a different wavelength. It's awesome.
That's a completely different sense.
I guess a lot of people, hearing is a better analogy. People have been using hearing as the sense, but it just blows me away that we can do that. So, well, cool.
I had a question. I think it resonates a little bit with some of the questions that came in. So we should be able to do the math with the number of light years and the scale that was on that image. So that's a good homework question. But we could cheat and just ask you, what are the linear scales of those orbits we're looking at? And then we'll go home and calculate it, make sure you're right. But anyway, we were trying. People wanted to know what's that scale, and also the amount of distance that. So there's stars in the orbits, but also that gas cloud moved, as you've been watching it, and how far did it move, sort of in a linear scale?
Right. That was from Jimmy Hebb. He was asking, how far did the gas cloud travel?
What is the closest approach of
a couple hundred AU?
Okay. Yeah. So the gas cloud got to within a few hundred AU of the black hole. So it's like in the outer solar system, right, for us.
Wow.
It's very close. That's about the same distance, actually, that one of the stars that has the 16-year orbit around the black hole gets to the black hole as well.
Yeah, it looks very close. About one, yes.
The closest star that is one whose orbit we haven't completely seen yet, but it came within something like 80 AU. As it passed the black hole, it was moving at about 4% the speed of light.
Wow, that's amazing.
A star moving 4% the speed of light. That boggles my mind.
Yeah.
That's amazing. That's very cool.
So this is from Twitter, at making sense, or at making sense. Sorry, I was split. I'm not sure I understand the question, but I'll read the words anyway. How does that work out in terms of star gravity interaction in the center? Stars colliding to form big black star or a black hole. So I guess the way I read that is, does that happen? Here it is. Scott's got it up now. So star gravity interaction. So do these things collide a lot in the center around the black hole to form bigger stars, in addition to falling into the black hole?
So there's several ways stars can collide and merge. The collision of stars will probably not form a black hole, but they will form bigger stars, and that's always interesting, right? So stars can collide from they just come at each other and then they collide, and then sometimes the collisions are at the right angle such that they can merge. Most of the time, they will sort of graze each other and sort of destroy parts of each other, and then they'll fly away. There's also special situations where if the stars was a binary, the binary separation can change because of the dynamical interaction with either the big black hole or with other stars. And when you can take a binary and squish it so that the separation is basically so small that they touch each other, then you have something called merger, right? So I don't know what the merger timescale is, but the timescale for stars to just randomly fly around and merge is kind of about one every 100,000 years or so.
Really, I didn't think it'd be that much. That's a lot. Okay.
Yeah, it's surprisingly high because the density is just so high.
Right, I guess so. Yeah, sure. That's funny.
The stars that are the sitting targets are, of course, the red giants. And the stars swell up to become a red giant, and then
they're just asking for it, aren't they?
They're asking for it, absolutely, yeah. And there's been some work on how what happens when a big fat red giant gets hit by a small star. Basically, the small star just goes through it because the atmosphere of a red giant is so thin.
Right.
And the speeds that stars are moving in the galactic center, the star is moving through it at several hundred kilometers per second. It doesn't affect the small star at all, but the red giant has its atmosphere stripped at least along the trajectory of the star.
Nice. Small star would be like, what? And then
I now have your new meme. Is it gonna be small star be like, what?
Small star be like, what? And the big star be like, hey.
Well, I know what I'm doing this afternoon.
Well, Hans Milling is asking a really interesting question. I'd like to see if you guys can answer this one. He's going, how far up meaning in reference to the disk of the galaxy, should we send a camera/telescope to be able to view the galaxy center without looking through the disk of our galaxy? So let's say
a long way.
Yeah, we just wanted let's not just forget how long it would take. Well, how far up would we have to go?
You would keep looking up, and you would just.
Oh, good, nice, very nice.
Thank
I
you.
like how you worked that in. That was good. And is there any advantage to that? There's got to be an advantage to be able to look at our galaxy from a higher.
Yeah, so our galaxy, the thickness of our galaxy is, if from the middle to the top, is about 100 parsecs or so.
About 300 light years.
Yeah, about 300 light years. So if you can go above the galaxy 300 light years, that would be perfect.
That'd be
you could do so much more astronomy, by the way. So I am all for that plan.
You're all for that. Okay, good. All right, cool.
I'll go get the TARDIS ready, and I'll meet you guys over at UCLA, and we'll just hop out there and take a look at it. Stop by Gallifrey on the way back.
That would be perfect.
Yeah,
I always think, in sci-fi, they should do way more astronomy. Like, why isn't Doctor Who?
I know, right? They have these starships and warp drive. What the heck? Why aren't they doing all this really cool astronomy?
We could literally have JWST inside the TARDIS. Just open up the doors.
Exactly, yeah.
It's bigger on the inside.
And boom, there it is. Speaking of JWST, and that's where I want to end this, there's a question up here from Chunky Chest again. Damn it, I shouldn't have said that. Okay, he wants to know, and this is a good way to end the hangout, would be, what about JWST, and what will it help you in your research with the Galactic Center? Because it's primarily an infrared telescope. Are you looking for a higher resolution? Are you hoping to learn more with JWST?
So there's a lot that JWST can do. It's bigger than Hubble, so that helps, right? So the larger the mirror, the higher resolution. Yeah, but also it has longer wavelengths than Hubble, right? So the images that we saw today from Hubble stops at 1.6 or so microns, but JWST will go much longer wavelengths than that. In particular, JWST were really great at seeing wavelengths that are very difficult to see from Earth, just because the telescopes and the instruments all are glowing, basically, as you get to longer and longer wavelengths. So it gets harder and harder to see the stuff in the sky as you get to longer wavelengths in the infrared. And so JWST, because it's cooled and it's way far away from the Earth, will be able to do all of that. And it can see, this gas cloud thing. There's lots of these objects at the Galactic Center, actually. And they are bright at long wavelengths. And so right now we're just on the verge of knowing about what is inside of them, but JWST should tell us, could give us a very good answer.
That's so good. All right. Well, with that, I want to thank you both, Dr. Mark Morris and Dr. Tuan Do, from UCLA's Galactic Center Group, from taking time out to talk with us about this amazing new Hubble observations of the center of our galaxy. And you promise you'll come back when you get more observations, right?
Yeah,
Sure,
we're always
pleasure.
looking at the galactic.
Yeah, I
center.
led you into that.
Okay,
I gave you
I'll
no
ride my
choice but
bike
to say
down there,
yes.
and I'll drag him.
Yeah, I gave you no choice, but that's right. Scott's in your neck of the woods. He'll come
Right.
over.
Come on down.
That's right. He will. Okay, good. All right. Well, thank you both for taking time out to talk with us. And Carol, what about next week? Do we have anything on tap, or is it a surprise?
Oh, surprise.
Okay.
We're
Well,
having a surprise.
yes, it'll be a surprise. Good. Well, we hope you guys will join us.
Stuff, more massive things.
More
We're on a
massive.
massive. First, we were on a gravity thing. Now we're kind of on massive things.
Small star be like, what? See? Okay. So
I'm going to cut that in the video, make it into a vine, and it's going to explode.
Big.
All right. All right, folks. I want to thank everybody for watching. We'll see you back next Thursday at 3 o'clock. If you haven't subscribed to Hubble Site channel, do so immediately and get rewarded by seeing more of these. So we thank you all for watching. Thank you for your great questions and comments. On behalf of Scott Lewis and Dr. Carol Christian, I want to thank you all for watching. And as always,
Keep looking up.
Thank you. It required maybe an addition of an observation of an additional filter to round out the color suite to really demonstrate the astrophysics. In some cases, it was just reprocessing the data and putting together imagery that was really engaging. Also, the group has done things like we observed the comet that went by Mars, a few other comets. We've observed Mars at close
was one of the most recent ones, if I recall.
Right, and a couple of other interesting phenomenon that sometimes amateurs observe as well. And we also have had activities often associated with our releases. And I have to say that in addition to getting additional data or bringing data forward from the archive, there have been a lot of scientists have done science on those observations as well. We're doing quite well as far as science productivity. So we have great public interest, science productivity, and really pretty images. So what more could you like?
That's right. What more could you ask for? Okay, well, great. So, yeah, the Hubble Heritage is a really important project that's going on at the Institute. If you've ever seen some of the really gorgeous, beautiful images that have come out, this particularly last over the Hubble 25th anniversary, a lot of them were due to our friend Zolove and the Hubble Heritage team. So that's very good. So that brings us to this particular image for today. A press release came out about the another set of Hubble observations of our galactic center, and here to talk to us about these images and so much more in the center of our galaxy are today's guests from the University of California, Los Angeles. Apparently there's a group there. And what they do at that group is they look at the Galactic Center. See, it's right there in their thing. It says Galactic Center Group. And joining me is Professor Mark Morris. He is a professor there, as well as Dr. Tuan Do. He's also a research scientist there. Welcome, guys, and thank you for joining our Hangout.
Hello.
Yeah.
Hi. I'm here.
And it's actually kind of chilly out here in LA. It's only like in the
I
upper
don't even want to
60s.
hear it. Don't even start with how chilly it is. Oh,
It's been kind of chilly. It's like 25 out.
Oh, jeez.
yeah, nice. Okay. Well, I'll just ignore what that is all about. So, we were talking a lot earlier before the Hangout started about some of the background of these images and some of the observations that we're doing, and we're going to get to a lot of that today, but these guys were telling me there's an awful lot of interesting stuff going on at the center of our galaxy, which some of which you've learned about already in previous Hangouts and other sources at Hubble site. But one of the important points is that the Hubble Space Telescope has been looking at our galactic center for a long time, and since I think 2005, according to some of what we talked about earlier today, they've been looking at various epochs. I've been going back and looking.
And we can keep you guys coming back for more science.
Yeah, that's a good point. I'm glad you brought that up. And if you want to find out more about these Hangouts, then the best thing to do is to subscribe to the events page on Hubble site or Hubble Telescope on Facebook. That's the best way to do it, and that way you'll get notified, and you'll get reminded when they're going to be and when the next ones are as soon as we know what they are. You can also subscribe to the Hubble site channel on YouTube. That's another way in which you can find out about all of these things. So do all of that, and if you're not following Hubble Telescope on Twitter, then are you really a Hubble hugger? That's the question.
That's the
So,
well, and I want to point something out real quick as far as the live chats. We have a very special guest in our live chat today. We have Zolt LeVay is in our live chat. So if you've ever loved any of the Hubble images that have been released, you can thank a large part of it to Mr. Zolt LeVay. He is a fantastic wizard when it comes to putting out our images.
that is a great point. So this is actually something that I think came out of the Hubble Heritage. He works on that, Zolt does. And Carol, what is the Hubble Heritage? Can you give us a little background on what that is?
Sure. A number of years ago, a group of us, including Zolt, were noticing that there were a lot of images and a lot of data in the archive that were being used for science, and some of them were really spectacular imagery, and if we could bring those forward to the public, we would like to do that. Sometimes
Hello, everybody, and welcome to this week's Hubble Hangout. My name is Tony Darnell, and today we are going to be talking with astronomers who are using the Hubble Space Telescope to peer deeply into the center, into the heart of the Milky Way Galaxy. And we're going to be learning all kinds of new things about what they're finding, because they've been looking using Hubble periodically over the past 10 years or so. They've gone back and looked at different things, and we're going to talk about what they're finding and the new research on the center of our galaxy, as well as the supermassive black hole lurking within its center. So we hope you will stick with us, and I have a lot of questions for our guests. But before I get there, let me introduce my co-host, Dr. Carol Christian. She's back from Paris, joining us now. Hi, Carol.
Hello, how are you? Sorry I missed last week.
Yeah, we missed you last week. I guess you're over your jet lag by now, right?
Oh yeah, It was a quick trip. It was painful, but it was a good trip.
Yeah, I heard that you didn't get to see as much of Paris as you had hoped. Well, we're glad you're back, and we're glad that you you had a good meeting. You were doing a lot of work for, I think, the future of a lot of research going on with the younger scientists. So that's really cool.
Next generation space leaders, and some other groups as well. Young professionals, yes.
And you're not talking about people going out and take me to your leader. These are actually people leading in space.
We're talking next generation, so we're like Picard and Geordi. That's where I'm going.
Good.
Right. Yes.
Yes. And speaking of next generation.
Yes.
Speaking of the next generation, here is Scott Lewis. He's also joining me back to drive the internet and drive me crazy. Hi, Scott. It's good to have you. It's good to see you. Welcome back.
Thank you.
And so we want you, before I introduce our guests, I personally want you, but I also think everybody wants you to also leave questions and comments for us and our guests for the Hangout, because we've got them for the whole hour. And Scott will tell you the best way to do that.
The best way, that's what I'm also here to do. So the easiest way right now while we're live is I'm seeing a bunch of people in here already. We are using the live chat on YouTube. This is a YouTube live event. So I'm seeing everybody saying hello. So hello, everyone. And people are already welcoming you back, Carol. So they missed you as well. We'll also be live tweeting using the hashtag Hubble Hangout. So I'll be keeping up with the pictures from the press release, maybe some of the videos that are going on. So if you have any questions or comments for the panel or anything regarding the press release and what's going on towards this really awesome cluster at the center of our galaxy, please go ahead and tweet at us with at Hubble Telescope or with the hashtag Hubble Hangout. Leave comments in the live chat, and also I'll be checking out the Facebook event that we have set up for it. I see a bunch of you guys RSVP'd, so it's great to see you guys. Hopefully subscribing to our events so you'll be notified whenever we set them up.